Good afternoon. My name is Mitch Robertson. I'm the Director of Enterprise Systems at Curo Financial. This is a project that's kind of near and dear my heart. It's based on a question that we ask often during interviews. What happens when I type www.google.com in the browser? We want to really talk about the value of wired data and why it's important to monitor the data that passes across your wire. So this series is going to start talking about those kind of things, and this is the longer presentation in one of the series. And we're going to get started with it and see how it goes. We hope people will enjoy it and hope you have time to watch the whole thing because this is going to be a little bit longer one. So lots of fun. The value of wire data. When someone obtains a strong foundational knowledge, so the value of this wire data is based on the fact that somebody has a strong foundational knowledge. This foundational knowledge is key to understanding it. So you hear me talking about foundational knowledge, but what does that really mean? What is foundational knowledge? Foundational knowledge is often people use the analogy of a house, building a house, building the foundation for the house, those kinds of things. However, I think that misses the point to some extent. Think about EMS, first responders, EMTs, EMT intermediate, paramedic, ER nurse, ER doctor. Within EMS, emergency medical services, all of these people play a role. The interesting thing is all of them are trained the exact same on certain things. They have the same skill set as one or the other. So a doctor who spent years in college and years training and years in internships does the same thing as the first responders do when they first see a patient. They always check airway, breathing, and circulation. That's a foundational skill and foundational knowledge that they have to verify before moving on. So we're going to start talking about that from an IT perspective. All of the curriculums I've seen always have the same classes in them. No matter what, a developer curriculum generally always has some sort of basic networking class that's taught. Systems administrator, basic networking. Security administrator, basic networking. Network administrator, basic networking. See a theme? Remember the OSI model, layer 7? I know a lot of people have heard it, but oftentimes when I get to talking to people about wired data, they really aren't thinking about the layer 7 model. Many people talk about layer 1, 2, 3, and even sometimes 4, and are more concerned about the routing of that data or how it's being routed. But the fact of it is you get an enormous amount of information if you start pulling the layer 7 data off and start analyzing it and getting information from it. So we're going to start this, and we're going to talk about it from the perspective of what happens when I type www.google.com, more or less from a TCP stack perspective. I know there's a lot of things happening within the code, and I know it's possible for it to travel through the code stack and things to happen at the code stack before it gets to the networking stack. But the truth of it is that in order for everything to communicate, it has to do these things almost always. The majority of applications today will walk through this process in some way, shape, or form. Name resolution has to take place. If name resolution doesn't take place, we fail. The minute you type that in your browser, I don't care what your browser is, it's going to go try to do name resolution. Once it has name resolution and has an IP, it's going to try to do a TCP three-way handshake. Once it's finished that TCP three-way handshake, now it actually has a TCP connection. So it's already connected at this point. Now we're going to do a TLS handshake because, again, Google's moved to HTTPS for everything, so they redirected to HTTPS. And it's going to go through that three-way handshake or that TLS handshake. And we're going to talk about that one. We're going to talk about all these in depth over the next couple of months. Once it does the TLS handshake and it has everything set up for encryption, then it actually starts up with HTTP requests and response, just like a normal port 80 HTTP request response stream. And then at the end of it, it sometimes finishes up and it might be a fin, might be a reset, just depends on the developer. You never know, and we might get into that a little bit more, but we'll definitely talk about all these. But to get started, I'm going to really spend some time talking about name resolution. In general, all systems will go through a name resolution process. It goes through and looks to see if it's itself. It goes through and looks to see if there's anything in the host file that tells it the IP address it's supposed to connect to. Looks at local cache. LLMNR, link local multicast name resolution, might get involved depending on settings on your computer. If you've got some old settings in place or haven't turned on some things, or off some things, NetBIOS might come into play. WINS, Windows Internet Name Service. It's funny, I laugh at it. Microsoft, I think, has been trying to get rid of this for years, but it's still out there, and I still run into environments that have WINS servers set up. Ideally, we should be getting rid of all those, but they're still out there occasionally, so that comes into play. And then last but not least is DNS. We actually make a query for DNS, and I'll get into that a little bit more. I'm going to spend more time on DNS, talk a little bit about the host file, a little bit about the local cache, but then I'm going to go right into DNS because a lot of the newer systems just really look at itself, host file, local cache, DNS. So we'll spend some time going in there. We'll talk about the value of that data. We'll talk about some of the things about the time to live, answers. We'll kind of explain DNS round robin. I'm not sure I'm going to get to that one in this video. We may talk a little bit about enhanced DNS. We'll talk about some DNS security things. Then we'll demonstrate in RevealX how we can see this at scale. And if you've watched some of my other videos, you may have already seen some slides on that. Host file is generally located on a Windows box, Windows System 32 drivers, etc., commonly used by attackers to circumvent DNS monitoring or DNS altogether. It may not be monitoring that they're trying to circumvent, they're just trying to circumvent DNS and get you to connect to what they want you to connect to so they can get that man in the middle going. There's a lot of other things that they do with the host file, but that's just one of many. Can be edited, but must have admin rights on most machines. You can use Notepad to edit it. You've got to open it with admin rights, make your changes, drop the file back in place, save it, you're done. Then things will use that instead of DNS. Cool testing tool, use it a lot more than most people think, but it's a great way to test things to see how they work. Local cache, all you got to do is ipconfig display DNS on a Windows box. I'm sure it's different on a Linux or a Unix box, but you can see everything that's in your local cache. You can clear your local cache by ipconfig flush DNS. I've been in situations where people thought ipconfig flush DNS actually flushed the cache on the servers. It doesn't. It's a different process to flush the cache on a DNS server, but there is a cache on a DNS server as well. So think about your time to live. You have a time to live in the cache on the DNS server. You have a time to live for the local cache. Quite a few things that happen with that, and we can get into that in more detail in some other slide decks as we go through. We're going to talk about the DNS packet. Right here we have two packets. We have the standard query for www.google.com, and we have a response. Here's the DNS request. In the DNS request, we have some cool information. We have this transaction ID. Always good to know. We have the request or the query itself for www.google.com. We can tell what type it is. It's a host record or an host address. And then we can tell it that the response is in packet 72. Good information to know if you're troubleshooting with Wireshark, quick and easy, right? In the response, we have that same transaction ID, and that's going to come into play in a lot of things as we talk through this, right? We have the question, we have the answers, we have queries. Again, it replies with the query that was originally made. So some people believe in just capturing the responses. Problem is this won't tell you when you have a request that never gets an answer. So really important to see both requests and response. You can get a lot of information out of having both. The answer, it is either answer or answers. In this case, you have a single IP address. So we have a single IP address right here. We have a time to live. It's always amazing that you see Google having a time to live 172. We'll talk about that a little bit because I've got some other slides that talk about people having times of 0 and wondering, what's going on with that? But we'll talk about that later. So here you have a DNS response with multiple answers. And right there you see that time to live of 0. This is Cisco AMP. trying to check in, and it has multiple answers. And if you actually were to open this packet further, there's 5 answers in this. And that creates a whole nother ballgame that we can talk about later on. But this is just the answers and the responses, right? So could having that time to live cause this in an environment? Is that possible? Absolutely, because all my clients wake up and they go, hey, I need to check in, and they all check in at the same time, and because there is no DNS cache, it queries, every single client queries and gets a response back. So we have 4,000, 5,000, 6,000, 10,000 queries. Now, if you think about how the DNS environments are often designed internally to a company, they often have your clients hitting internal DNS servers, and then those internal DNS servers forward that query out to something else. So what ends up happening, instead of having 10,000 queries for my 10,000 clients, I actually have 20,000 queries. This, not necessarily good for all environments. Maybe if your environment's set up to handle the load, maybe not. Is it a good idea? Should Cisco redesign this? This goes back to that Google question. Google's got all of these thousands and millions of people hitting their environment, and they have one IP address. Why does it take 5 different answers to get high availability? And a time to live of 0, which causes an additional hit on my network. I don't have an answer. I'm not sure why they do this. I know why oftentimes they set DNS up so it has multiple responses, because they have intelligent clients that randomly pick one of the 5. And that's really cool, and it can actually, I don't know whether AMP can do this, but some clients I've seen, Link does this, will actually take one of them out if it doesn't respond. Exchange does this as well. So if it has 5 responses of SMTP servers it can go to, it'll take one of them and go, I'm not going to respond for you for the next 5 minutes because you didn't give me a response back, and it'll try the next one. And so it randomly tries these different ones until it gets through all of them. But that means I don't really need a time to live of 0. Ooh, is it possible that my time to live of 0 is less because as it comes through the server at 5 minutes and it gets to the cache at 5, and by the time it comes to me, the packets that I'm seeing are only at 0? I don't know. We may have to dig into this further. Pretty cool stuff. How about a DNS timeout on the server side? This is kind of cool because you can see that this client, this client kept querying for almost 10 seconds. Not quite, almost, more like 8. Eventually the server timed out, or the response ended and didn't happen anymore. So it timed out because it never got a response back. But that's what it looks like. So based on timeouts, I started thinking about this a little bit further and thought, well, I really want to see what is the client timeout for a Windows box. And I'm sure it's different depending on what operating system you have. But as this says, Windows 7, Windows 8, with a single NIC and a single DNS server in the NIC, this goes through the process. So 0 seconds, client queries the DNS server. 1 second, client queries the same DNS server, and it goes through that entire process of querying that same DNS server multiple times until it gets to 10 seconds, and then it stops querying. That's interesting. What about with 2 DNS servers? Client queries the first DNS server on the list, waits, doesn't get a response. 1 second, it queries the second DNS server, waits for another second, client queries again the second DNS server. So it's not querying the first, it's querying the second. Okay. This time it waits 2 more seconds. Client queries all the servers at the same time, so it makes a query to both servers. During this entire process, it's keeping the same transaction ID during this entire process. So both servers see the same transaction ID. Because ultimately, from the network stack, it just runs the response back. So it's using that same transaction ID all the way through. At 4 seconds later, it goes, hey, I'm going to try again and send it to all the servers in the list one more time. And then at 10 seconds, it goes, hey, I guess we're done. No more queries. At least that's what you'd like to think, and we would hope that would happen. Problem of it is That's the response from the network stack. What happens with the application? When the application doesn't get a response after 10 seconds, what does it do again? Oftentimes it queries again and again and again and again and again. So you end up having thousands of requests because it never got a response back. That actually can cause more damage than getting an error back. Because if it gets an error back, oftentimes it'll pause at least for a little bit. Not always, it depends on the application. And then if I have 3 or more configured, go through the same process. Ultimately, once I get past the third one, then I query all the servers. So it's still 10-second response time. So here's what gets interesting about that, because when it stops that query, it closes the client port. In this case, it's ICMP that actually returns a response, has nothing to do with DNS. It returns a response that says destination unreachable, port unreachable. And what port is unreachable? It's the client port that is unreachable. Interesting. In the ICMP packet, it maintains the transaction ID. So now I can match that to a request that failed. 10 seconds is a long time. I would kind of want to know if my clients are timing out and closing the port. I'd want to monitor that. Cool thing is, with ExtraHop, I can. I don't think I have a dashboard picture in here on this, but at some point I'll actually put that in a presentation so people can see it. It also has the query that was made that ICMP is responding back to say, hey, I'm no longer available. I'm not taking your response. And it shows the answers that were sent back, right? So that information is being sent back, and the ICMP is going, port closed, I'm done. You didn't get to me fast enough. Is that an issue? Could be. Something to think about. What happens when a client goes off the rails? So when a client goes off the rails, this can be a really bad thing. And when you're watching this at scale, when you have all of your clients and you see all your DNS transactions, you'll start to see things where DNS requests get higher than DNS responses. You can see that blue line getting larger, and there's more requests than there are responses. Got a DNS server that's starting to have a problem. It continues to happen all through here, even a little bit here. What's happening? Notice up here, our processing time is actually getting worse. We're out to 500 milliseconds on server processing time. That's not good. That's on our 95th percentile, so that's still not bad because it's your top failures or your top worst case processing. But you can see it's getting worse than it has for any time, and you can see that my 75th and even my medium time are all coming up, which is not normal. So something's going on with those servers. That potentially is a problem. But I can see that. I can get warnings on this. I can get alerted to. I can react to this and do something about it because I know that's happening. How many people actually know this is happening in their environment? I've been in hundreds of environments, and very few of them had the details and had the capability of telling me that this was happening. Do you think this is causing problems with applications? If applications are querying and they're not getting responses down here, do you think that's going to be a problem? I think so. I think it could cause some unknown issues that you might be chasing your tail on sometimes. So in this case, a single client caused this problem. The interesting thing is you can see up here where it was doing a query every hour or so. So the record was there and it was querying every hour or so. But all of a sudden, things started going wacky right here. And this was from a single client. I'm going to have to see whether I can get this picture blown up. But that was a single client that started doing all of these additional queries. Interesting. Funny thing is we were sending out responses. What do you think might be happening at that level? So if it's querying for something and it's getting a response back and it's querying it again, is it possible that there's something happening? Is it possible that servers having a CPU issue or a memory issue? Problem with the network stack? Could it be hung up? Yes, this kind of stuff actually happens. Could it be a kernel mode memory problem? I want to think about that. This is a way that I can actually start to give some indicators based on wired data related to server performance. Potentially, this server had an issue either with CPU, memory, or kernel memory, or the network stack itself. So now it's time, it would be time to go investigate that specific server and see what might be going on. Pretty interesting stuff. I'm using wired data to point me to the server and potentially give me things to look at right away. Single client taking off on its own. Here we go. This is it. Right there. It's querying for this secure communityclients.com, right? Not good. Single client. Other clients are querying for it, but they're getting responses, and you see they don't query again. Good stuff. Here's monitoring at scale. This is something that I have the ability to do with RevealX. Any of the extra hot products give you this ability to dig into this kind of data at scale. So during this time period, which I believe was a 30-minute time period, I can see that I had 381,000 requests, right? I only got 284 responses. So potentially a problem. 2,000 of those were request timeouts. Interesting. 83,000 were errors. And here's some of those errors. There's this request for this domain, this domain. There's a bunch of reverse lookup queries in here that are happening. Those are good or bad? Don't know. Don't know. Might need to dig into it. Here's the host bandwidth right here. What's my biggest response? This is from those Cisco AMP clients. And then I've got all my types of records and how many are queried at a time, what's queried the most often, CNAMEs, text records, any record, other records. Those are things you want to pay attention to when you're monitoring your environment. With RevealX, it gives me the ability to see this pretty quickly. So some of the next presentations that I'm going to work on is the TCP three-way handshake. Explain the handshake, the TCP flags, demonstrate the handshake. We're going to show packet data. We're going to show some of the same information and why it's valuable and how we can see it at scale in RevealX. We're going to also dig into the SSL handshake or TLS handshake later on in another presentation. Get into SSL and TLS versions. How do we find them? How do we see them? What's important? What's not? Discuss certificates, ciphers, CRLs, OCCP, OCSP, trusts, key size, issuer. We're going to dig into this. We're going to show it in packets. We're going to show how it looks in RevealX, so show some of the value in it. It's amazing what you start to see when you have this at scale and how fast you can find TLS problems in your environment. We're going to spend some time talking about HTTP, the requests, size of the requests, speed of uploads, speed of downloads, explain the ACK received after data uploaded is important for measuring turn times, HTTP response, size of response, speed of response, HTTP codes that can be returned and the value of them. Why is that important? We're going to show it in packets. We're going to show it in RevealX. Hopefully it'll turn out pretty good. Pretty cool stuff.